start today's lecture. So last time we were here, I think, trying to go over some of the probability review, and we stopped at an exercise of dealing with the transformation of variables. Okay, so let me just put it up. So we have the formula that we reviewed, and then also get to the point where we were trying to do the exercise. Right. So this is the general transformation of variables. And last time I was saying that the reason why we care about this, is because a lot of times you have a density of a particular random variable or parameter in the model, but sometimes you care a different formulation of that. Say, example that I gave last time, I think is like sigma, which is the standard deviation of a normal. If we know that follows a particular distribution, then sometimes we, okay, good to know. All right, so I was saying, so sometimes you might be given a density or distribution for a random variable or parameter, say the standard deviation, but a lot of times maybe you care about sigma squared. So we care about, well, if I know the density of sigma, what would be the density of sigma squared? So in this case, from sigma to sigma squared, this particular gx function is x squared, right? Yeah, so just for the example that sometimes we are given density of a particular parameter, but you might care about a different one, so a function of that one, and that's why we're doing this review at this stage, right? So again, if you have a continuous random variable x with PDF fx, check that if it's monotonic and differentiable. I should say it's the function itself, whether it's monotonic and differentiable, and if it is yes, then you are able to write the PDF of this gx function through this formula. Okay, so keep this down, write this down on your note, and then we're gonna get to the exercise that we left at last time. So suppose x is a uniform between 0 and 1, and we're asking you how to come up with the gx function. In this case is negative ln x. Okay. So check if this gx is monotonic differentiable. I plotted here for you. And then if it is, try to figure out the density function of y. So we can just pause here. You can work yourself, and you can also check in with your neighbors if you get an answer, or if you're stuck somewhere, I will just walk around and help out. Yeah, maybe really quick over here. So we do know that y is negative ln x, so that's gx, right? And in order to find dx over dy, you should express x in terms of y. So you need to find the inverse function and then take the derivative.
Okay.
Oh, excuse me.
Yes.
Yeah. Yeah. So that's my name. And just keep working on it. Okay. So maybe we can look at it together. So first of all, you need to check if it's monotonic or differentiable. In this case, both of them are. And then we go to the inverse function. So you can use this notation g inverse y. And then what we have is, because y is negative ln x, so x will be x1 negative y. Okay. And then from there, well, this is what calculus, differentiation, the rules come in, that you will have dx over dy to be negative e to the negative y. Okay. So when you take first order derivative of ex will be ex, right? But then you have this chain rule, because you have negative y here, and then you take this, sorry, then you have the negative sign front, then the exponent is still the same. So there's that. And once you get that, don't forget that you should think about the range of y. So y itself, because it's as it is negative ln x, so an x is uniform. So y will be from 0 to infinity. And then we're able to apply this here. So this is the formula that we covered, but we need to be careful using it. So first of all, fx is 1 because it's uniform between 0 and 1. Okay, so that's where we're hidden. You should know that. So fx is 1. when x is between 0 and 1. And then also, we have to take the absolute value of the dx over dy, and then that becomes e to the power of negative y. Okay? And you probably don't know about this distribution yet, but later in the semester, we're going to cover this particular distribution. So if you have a density f of y to be e to the negative y, then it is exponential distribution with parameter 1. Okay? So just so you know, it's exponential distribution. So if you start with a uniform 0, 1 for x, and if you're looking at the gx to be negative ln x, then your y is exponential 1. Okay? So make sure that the technique, you feel comfortable about it. There is one homework question for you to practice, so hopefully you get more exercise along the way. But then during the semester, you will see at various places we apply this in order to make sure that we know how to do transformation variables, and then in particular, if we're curious about a function of a particular parameter, and then we care about the distribution of that, we can derive it based on this rule. Any other questions here? Yes.
Sorry, can you just repeat where the 1 came from?
Yes. Yeah. So based on this formula, we know that we need to have f of x.
Yep.
So that's the density of x, PDF of x. And then x, because we know that it's between 0 and 1, is uniform. So let's see. So if you have a random variable x, which is uniform between a and b, then f of x is b minus a. No, is 1 over b minus a. Right? The density. Yeah, so in that case, because b is 1, a is 0, so for the uniform between 0 and 1, the density is 1. Okay.
And then for that exponential, just maintains that, and that's why the 1 is in the bottom.
This one? Oh yeah, here. Sorry, can you repeat? I couldn't hear this.
In the bottom right corner for x with 1.
Yeah, that's it. Yeah, this is exponential distribution.
With mean of 1.
With the rate parameter 1. So we're going to cover that later. But for now, when you're looking at this, just so you know, it's exponential distribution with a particular rate parameter is 1. Yeah. Yeah, so good question. I guess I was pretty fast going through this. So if you have a uniform distribution A to B, then the density, a continuous uniform, then it's 1 over B minus A. So it's 1 in this case. I guess it's slightly easy in this case. The homework question, I think, slightly more involved, but you probably know the results because it's really just doing a standardization of the normal distribution to the standard normal. Okay, so you know the results, so try to work it out to see that it is indeed a standard normal distribution. All right, and then just last few definitions before we move to the new chapter. So first of all, we care a lot about independent random variables, and in particular, later you will see in the semester that we care about what we call conditionally independent. So let me just talk about the definition first and then put in the context. Suppose y1 to yn are random variables, and theta is the parameter describing the condition under which the random variables are generated. To give you an example, if you think all of the y's, they follow their random variables following a normal distribution, then the theta can be the mean, can be the variance, and can be both. Okay, so those, you can think of those random variables following a particular distribution that we're gonna cover later. And then theta is a generic term for any or all of the parameters in that statistical model. We say that y1 to yn are conditionally independent given theta if for every collection of n sets of a1 to an, we have this form. So the independence comes into play when you see that, well, we're really on the left-hand side, we're considering the joint distribution, right? The joint of y1 to yn, and then each of this y, like into a particular set. When they're conditionally independent given theta, so you see that theta is always written after the conditional sign, both on the left-hand side and on the right-hand side. And the right-hand side, each of the term is a marginal, okay? So when they're conditionally independent, then the joint becomes the product of the marginal. Okay? So that's what conditionally independent means in this case. And we're looking at y1 to yn, they're random variables, and theta is the parameter or set of parameters. So under independence, the joint density will be the product of the marginal densities. So generically, you can write on the left-hand side, that's the joint density of all of the y's given the parameter in the model. Then because they're conditional independence, you can write the joint in terms of the product, the marginal, and very commonly you will see throughout this semester that we use this kind of notation. Okay. So because they're conditional independent, the joint becomes the product, the marginal. And each term, the conditionally independent, the conditional really comes into play because of the same parameter that we assume that those random variables generate based on. And then lastly, in this case, we will say that y1 through yn are conditionally independent and identically distributed. So this term you probably heard before, IID. Okay? And we will make this assumption a lot of times when we're thinking about how data are generated. So in this case, it's always conditioned on the y, sorry, on the thetas. So we always write it there. And you can write a little IID on top of tilde to represent this notation. Okay? Yeah, so maybe in some other stats course that you took before you have seen this. But again, in this course, we talk a lot about conditionally IID, and then we think about random variables jointly distributed according to a particular generating process. So in light of this, I want you to try one more exercise here. So suppose, so this is the case that I was telling you earlier, that if you're assuming y1 through yn, they're normally distributed, then the theta, the collection of the parameters, in this case becomes mu and sigma. Okay, because normal distribution has the two parameters, unknown parameters. So we're gonna replace theta with mu and sigma here. And then in particular, their IID, normal with mean, and standard deviation with sigma. Here, the exercise asks you to write out the joint density of all of the y's. Okay? I'm giving you a hint of the marginal density for any yi here. Okay? So because they're IID, and we also know what each marginal is, I'm asking you to try to do this exercise to make sure that you know how to write the joint from the marginal and how to simplify some terms. Yeah, Josh.
Okay.
Oh.
No, I was just gonna, like the previous slide, I couldn't see the bottom.
Oh, okay. All right. Yeah, let me bring it back really quick. I think it was because right, this particular thing, yeah, so nothing much below this. That's all I can say. So here is just y1 through yn. Given theta, it's IID Fy given theta. Okay, but for the future, I will make sure that I don't have too much in the bottom, so we get, yeah, thanks. All right, so here, this is the exercise for you to try it out. This is making sure that you know how to write the marginal in the first place, how to take the product, and you might be able to do some simplification when you're doing the product. Okay, this is a key skill to get in the Bayesian class, because later you will see a lot of times how we're writing the joint density of different random variables. All right, so here you can also write as 1 over 2 pi sigma squared e to the negative 2 sigma squared y pi minus negative 2 squared. Yeah. And also sigma in this case is the standard deviation, and we just use this notation for the system. All right, so if we look at it together here, I just put everything together in one note. And the thing is, there's certain simplification that you can do. So first of all, by the conditional IID, we can write the product, right? From 1 to n, because you have n objects here, or n random variables. Each of them is a normal. So if you keep the product sign here, and then each of this is a particular expression based on what we're given of the normal PDF, right? So typical simplifications for this type of manipulation is, first of all, So the product is governing I, subscript I, but then this first term has no i's in it, right? So typically we do 1 over or like whichever, but then raised to the power of n because you have n copies of this being multiplied together, right? And then in the exponent, then you will see that the product of multiple of this becomes the sign inside of it, sum inside of it. And because it's, again, the product is going over I, so yeah, to be super careful here, it should be I from 1 to n, and then it's yi minus mu, the sum of all of the squared. Yes.
Why can you pull the negative outside of the sum?
You
Because
mean
they're all
the,
gonna be negative, doesn't matter.
this negative?
Yeah, that one.
Yeah, so you mean like put it outside of the exponential function or?
Or like, I don't know, I guess in my head, for some reason, I feel like it should be inside the sigma,
Inside the sigma. Oh, I see. Oh,
but I
okay.
don't know
Right,
why.
right, okay. No, good point. So the thing is, I guess I always just keep the negative sign here
Mhm.
and then always just work on this one. So you have a negative sign here and then it will be the sum of all of the terms here. So, I mean, there are many ways, I guess, you can do this. The reason why I keep it this way, because later when we're doing a lot of those derivation of those distribution, it's better just to keep the expression more like what you saw before, because later you will see that in this course, we're gonna try to recognize certain distribution based on the expression. So for this case, I'm still trying to keep it based on the form of the normal, because later I will try to recognize in that way. Yeah, but you're right. I mean, we can always keep the negative, say like separate or into it. That's fine as well. Yeah, but good point. Yeah, again, I guess this is really like I had to think through what's important to review at the beginning, but then all of the material is linked to what we're going to cover later. So I guess the way that I kept doing this will be related to what we will be doing it later. But this is one example here. Make sense? Okay. All right, so in the homework question, I think one of them is also asking you to do more of this kind of manipulation, making sure that you know why, when they're independent, like conditionally independent, how you can write the joint density of a sequence of random variables. And lastly, once we have the joint distribution of all of the yi, we also define something called exchangeability. And I don't want to go to too much detail because it's actually pretty much involved. But for now, I think what we need to understand for this exchangeability is mostly about if you have a sequence of observations, in this case, yi through yn here. Yeah, by the way, we use capital letters to denote the random variable, and then the small letters to be the actual observation. Okay, so just keep in mind. And so when we're talking about exchangeability, it's more about, by definition, is if you have the joint distribution of all of the random variables, and then if you can come up with any kind of permutations, it's more like a sequence of 1 through n, and the joint density wouldn't change. So in short, it's just saying that all of the observations, in this case, the random variables, they can be exchangeable, like they can be anything, because they all just follow marginally a particular distribution, and then you put it together from the joint density. And that's the key of this. And you will see that we make this assumption throughout. So later you wouldn't even notice this exists. But this is one of the fundamental assumption when we're thinking about the generating process of random variables from those processes. Yeah. And later you will see certain ways that we talk about those exchangeability ideas in the models. So I just put them here, but I think it's probably a better idea we move to the actual, like one example of models that we're going to work on in the second chapter. So we'll see more about how those definitions and those assumptions are being made. Okay. All right, so this is, I think, the end of the introduction. And